Today, let's design an idempotent ledger service. Imagine Alice sends Bob $50. The ledger commits the transfer, but the response disappears in the network. Alice's service retries the same request. Should the money move again? Of course not, but just check for duplicates is not enough. Two requests can arrive together. A process can crash between writes, and a different payload can accidentally reuse the same key. Our goal is stronger. One client intent must produce one durable outcome. The same retry returns the original transaction. A mismatched retry conflicts, and every committed transaction leaves the ledger balanced. This is an illustrative interview design, not Stripe's production architecture. We are building an internal single currency ledger. An authenticated client posts one transfer as balanced entries. It can recover the posting status, read a balance and ordered history, or correct a mistake with a linked reversal. 4 rules define correctness. First, the same client and idempotency key identify one intent for 30 days. Second, the request fingerprint proves whether a retry carries the same canonical payload. Third, every committed transaction sums to 0 in one currency. Fourth, committed entries are never edited or deleted. Suppose Alice loses $50 and Bob gains 50. Negative 50 plus positive 50 equals 0. The ledger records both sides together, or neither side at all. For scale, assume 50 million accounts, 20,000 posting requests per second, and 200,000 reads per second. Healthy posts should finish within 500 milliseconds at the 95th percentile. Reads within 200. A few accounts may be extremely hot. External banks, card processors, foreign exchange, fraud, credit, and disputes stay outside our boundary. This service records internal accounting truth. The data model needs to prove both the accounting event and the retry result. An idempotency record is keyed by client ID plus request 7K. It stores the canonical fingerprint, the current state, the final transaction ID, the stable response, and the 30-day expiry. Transaction 204 stores its currency, status, immutable ledger position, and an optional link to the transaction it reverses. Its entries store account, signed amount, currency, and account local sequence. The zero-sum rule lives at the transaction boundary. We can support 2 entries or 20, but they all commit together and their signed amounts must add to 0. A balance is different. It is a fast, versioned view derived from immutable entries. Its applied sequence tells the caller exactly how fresh that view is. If the projection disappears, the ledger still contains enough truth to rebuild it. Now, follow request 7K through the architecture. The gateway authenticates the client, rate limits it, validates the entry shape, and computes the canonical fingerprint. The ledger service routes the request to the owning shard. Inside one database transaction, the service claims client plus key. A new key continues. A matching completed key returns its stored response. A different fingerprint returns conflict before money moves. For the winner, the same commit creates transaction 204, writes both immutable entries, stores the terminal idempotency response, and inserts an outbox event. Only after that commit succeeds does the API say committed. That shared boundary is the heart of the design. A crash before commit leaves no transfer and no success. A crash after commit leaves the transfer and the exact answer needed by every retry. The outbox relay can publish its event more than once. Projection workers therefore use transaction ID and account sequence to apply each logical entry once. Caches may accelerate reads, but they never become financial truth. Let's stress the idempotency path. 2 identical copies of request 7K arrive together. A unique key on client plus idempotency key lets only one transaction own the claim. The other caller waits briefly, pulls the same status, or receives an in-progress response. It never starts a second posting. Now a request reuses request 7K with $60 instead of 50. Its fingerprint differs, so the service returns conflict. The key identifies the intent. The fingerprint verifies the payload. They are not the same thing. Next, the database commits transaction 204, but the network drops the response. The retry finds the committed idempotency record and returns the original transaction ID and response. No new debit, no new credit. If a worker dies before the atomic commit, the database rolls back the claim and entries together. If the implementation exposes a longer-lived claimed state, recovery must first look for a linked committed transaction before reclaiming it. Blind replay is never safe. After 30 days, the lookup record may expire under the documented contract, but the 7-year ledger history remains. Expiring retry memory never deletes accounting truth. Idempotency prevents one request from posting twice. It does not, by itself, serialize different requests touching the same hot account. Before commit, the service locks affected accounts in a deterministic account ID order, or checks optimistic account versions. Then it allocates the next account local sequences and writes every entry atomically. If two transfers compete for Alice's account, one wins the version. The other performs a bounded serialization retry using its original idempotency identity. It does not invent a new logical request. Unrelated accounts should not block one another. Partition by a ledger or tenant boundary that keeps common transfers local. If arbitrary cross-shard transfers are required, name a real atomic protocol. Never hide two independent account updates behind the word eventually. During overload, an account-affine queue and back pressure are safer than unlimited retries. And if the durable authority loses quorum across zones, it fails closed. A temporary error is better than two conflicting financial histories. The write path protects truth. The read path makes that truth fast. The committed outbox event carries transaction 204, its ledger position, and each account sequence. A projection worker appends history and updates balance only when it sees the next expected sequence. A duplicate event becomes a no-op. A gap triggers replay instead of a guess. Balance and history responses include an as-of position, so a caller can see that Alice's balance is current through sequence 41, while transaction 204 is already committed at 42. Transaction status comes from the authority even while the projection catches up. A reconciler periodically compares projected balances with the sum of immutable entries. If a projection is missing or wrong, it records an audit event and rebuilds from a trusted position. It repairs the view, never the ledger. Corrections follow the same principle. We do not erase transaction 204. We append transaction 205, a balanced reversal linked to the original. The full history remains explainable 7 years later. Let's return to the lost response. Alice's retry is safe because 4 boundaries work together. Client plus idempotency key names one intent. The fingerprint detects a different payload. The idempotency result, balanced entries, and outbox commit in one transaction. And every fast balance carries the position it has actually applied. Around those boundaries, deterministic account ordering handles hot writers. The outbox makes projection delivery recoverable. Reconciliation rebuilds derived state, and reversals preserve an append-only audit trail. If you remember one picture, remember 2 retry arrows entering one commit gate and leaving as one transaction. That is idempotency you can prove, not just hope for. You can practice the complete Stripe interview problem and compare your design with the editorial on FastPrep.